I think I'll discuss that a bit at the last lecture, but when you do real time, you actually typically don't fully solve the NLP problems. You often like kind of exactly you solve on the fly and not really to full convergence. That's very typical. And then you need to short circuit the NLP solver to do that yourself. Yeah. Okay, guess you can restart here. Maybe I can just very briefly, just to make sure that I'm not losing too many people, specify a tiny bit more what is happening here. So your H is a collection of H1 to Hn typically. And when you guess an active set, you're essentially collecting some indices. I don't know, if n is, for example, 20, you may guess that 1, 3, and say 11 are active. So it's a collection of indices. And then when you form HA, you're essentially stacking H1, H3, and H11 in here. So essentially you've selected a bunch of these constraints. And so nabla HA as the gradient of this constraint. That will be, nabla H1, nabla H3, and nabla H11. And you know that if the active constraints are these guys, then mu 1, 3, 11 are supposed to be non-zero, and mu of everything else, so 2 and 4 and all the way to 10 and then 12 all the way to the end, they are supposed to be 0 if the constraints are inactive, right? So once you selected that, you already know this information, and then you form this linear system, and you will be able to compute these guys. The mu a's, they are supposed to be non-zeros, and you are supposed to get, when you linearize that constraint, so this guy will be 0 by construction. It's part of your conditions. But the inactive ones, they are supposed to be less than 0. So you can build that thing and you can essentially check with these conditions that things are correct. Okay, so we can write a code that does this, and that's really what's happening in the QP solvers doing this kind of things. And I'm gonna use this prototype example. So you have a polytope that's you have to be inside this thing here, and the solution is so that's the free minimum down here, and you can visually guess that the solution of the QP is here, right? It's gonna want to go to the minimum and will basically be stopped by this constraint here. But for example, in an active set environment, I would maybe form a guess here. I'm gonna guess my delta W, that's my primal variables. I'll guess them up here, and I will guess that I hope you can see the colors. It's blue here and black here. Yeah, you see that, or is it okay? Yeah, okay, I'll point on the way. So I will guess that these two constraints are active, and that's coherent with my point here. And these constraints have indices 7 and 8. So my active set is 7, 8. I have a delta W that matches these two active constraints. I could form it fairly easily from that. And then you form this thing. So you collect the nabla H's that correspond to 7 and 8, and the HA's corresponding to 7 and 8. You will basically form that linear system, and that will give you a delta W. I'll call it plus. It may be different than this one, or it may be the same. I'll get a new lambda and a new mu, possibly. So I'll solve the system. And then what's going to happen, you'll go from this point that you guessed to this new point, delta W plus, the one you get from solving this system. Possibly it's the same point, then you don't move, but if it's somewhere else, you'll move towards that new point. And you'll move until you possibly hit a new constraint. If you hit a new constraint, you add it in the active set, and then you go through your list of mu's, and if some of them are 0 or they have the wrong sign, remember they should be positive, then the corresponding constraint, you remove it from the active set. So you check that index k for which you have this thing, and you remove that thing from the active set. And then you have an exit condition. If the mu pluses are positive, that's what you want, and the new delta W is the same as before, then you're happy with what you get. So we can actually, it's much easier to look at this in a visual way on the problem. So we'll basically do this problem here. So in that problem, I will guess that my active set A is 7 and 8. And if these two constraints are active, I would have to select that point. That's the only point that can match these two active constraints. So I have my delta W, I have 7 and 8, I form that system. And I calculate this. So my mu plus is 0.24 for that constraint, and minus 2.7 for that one. And my delta W plus, there's a plus in here, is also here, right? So I'm not supposed to move actually. So in that sense, this line 3, I don't do anything. I did not move my my W, so I don't need to add any new constraints. So step 3 and 4, I don't do anything. And then I check my mu pluses. If I have any negative one, and actually see that one is negative, it has a wrong sign actually. So what I will do, I will remove that constraint, that's constraint 8. I'll remove it from the active set. So I'll basically delete this number in my active set. Right, so I delete that number. And then I check my exit condition. Well, this failed. I had the mu plus with a wrong sign, so I cannot stop here. So then I will go back to my step 1. So I've updated my active set. I need to form a new system. So I don't need to recalculate these things. I just need to pick the ones that match my active set. So I'll reform these guys, reform the linear system, and solve it again. And so you see what's happening now. Geometrically, what's happening is that you gave this constraint to the solver. So it's actually going to the minimum along that constraint with respect to the cost function. So it brings you basically here. That's the minimum along this line here. So the system here wants to go all the way here. It's actually going out of the feasible set because remember, right, it's looking at this constraint as if it was an equality constraint. So the delta W plus, and yeah, that's what I get. So if I move my delta W, the red thing, along this direction, but I stop when I hit a constraint. So here I detect that I'm hitting this new constraint, so I bring my delta W here. I also, yeah, when I computed my system, it's not very visible here, I got a minus mu plus 7. So actually this constraint has the wrong sign on the multiplier. So when I reach this point, so here I add this new constraint in the active set. So I'll add number 6, and I will remove 7 from that. So yeah, I don't see the colors very well. I remove this one, it had the wrong sign on the multiplier, and I hit that constraint, so I'll add it to the active set, right? Essentially, you keep doing that for a few more rounds. So now you have this constraint here, you form the system with that constraint, it will make you move along that line here. It wants to go here. Mu 6 plus has the wrong sign, you will remove this guy, you will hit that guy, and you will add it in the active set. So you'll move here, remove this constraint, and add this one in the active set. And one more shot brings you here. This mu has the right sign, we'll keep it. But now when we move along this line, we'll hit that constraint, so we'll add it. And then we form the system again once more, solve it, and voila, you have the correct signs on both mu's, and the delta W does not move. So you met the exit criteria, right? Okay with that? So we had to do a few rounds of updating this active set and solving the linear system again and again, but it does bring us in the end to the correct solution. It's really all about identifying that, oh, now I've hit a new constraint, it will probably be active, or this constraint has the wrong sign, I'll delete it from the active set. It's essentially what is happening in these lines. Okay, so this strategy is very fast if you have a few changes of active sets, obviously. Here it was a very simple problem. We had a bunch of changes, but also chose on purpose a pretty bad initial guess. But if you have to change once or two indices, then it can be pretty fast. You may just do 2 linear solves or something. One theoretical issue is that there is no complexity bound on the QP in theory. So if I give you a QP problem that could be parametric, for example, you could not guarantee anyone that you can solve this problem without actually exploring every single possibility in the active set. We don't know any result like this, which means that in theory, this procedure could be awfully complex. In practice, we've never seen a problem that is awfully complex. What you see in practice when you use this kind of QP, for example, for doing MPC, is that you have quite drastic variations in the time you need to solve the QP. Sometimes you have very few changes of active set, it's incredibly fast, and all of a sudden it spikes to a pretty large computational time just because it had to go through a number of changes. And if you're in a real-time context, what matters is the worst case scenario. You don't care that it's usually very fast. If every now and then it takes half a second to solve, then that's the bottleneck you have. Okay with that? Yeah.
Like now you're moving from kind of corner to corner.
Yeah.
What if the optimal point is like in the middle of a line?
All right. In that context, it would not happen actually. You're not supposed to end up at the middle of a line. Okay, sorry. Unless the minimum itself is around there. In this context, what will happen is that the mu will have the right sign once you reach the solution. Mm-hmm. And the delta W will also not want to move. So you could end up there actually, yeah. Okay. So if I was putting my minimum such that, I managed to drag my point in between. Yeah, that's true. Yeah, so it would work fine, yeah. And so maybe if the solution was actually here, you probably would go through the same procedure, and here we'd want to jump here and stop here. And maybe that's an interesting observation. Once you have the correct active set, it converges in one step. Okay. So you get there, once you figure out this constraint should be active, I would just shoot here and realize it's correct. So that would stop here. Yeah.
That's a full step length then, instead of moving until hitting a constraint?
Yeah, because if you were to, for example, you had these two constraints supposedly active and you release that one and activate that one, you would, you would not hit a new constraint, right? So at this stage you would jump here. Yeah, that should work that way.
What happens if you start in the opposite corner of the endpoint?
Up here.
So that W plus will be directly perpendicular to the constraints, so you don't have anywhere to go.
But so I expect if I was starting the point up here, I think I could try in the code. I think the two multipliers would be negative, and it would release both constraints at once. And actually, then it's really nice because it would basically want to shoot here, and it would probably hit one of these two constraints, activate it, and then hit this point. So actually, if you start here, it would converge faster than starting here, most likely.
Do that in that corner? Isn't it faster in that corner as well? To just go
From that one? Or
that one.
So we try this one.
Yeah. If you instead send so to release both constraints, wouldn't that be faster?
Yeah, but you don't know if that's the right thing to do. Yeah, it's not obvious. Yeah, in practice because this is a very easy problem, of course, but yeah, I was trying to think of a way of showing that, but it's not obvious. But very often, typically when you have MPC, the activating active sets, it's like kind of a chain of things that happen. So you start from a point, and then you hit something, you change something. So you have to navigate your problem in some ways. It's not easy to explain that without all the background, but I think if you were to release everything, you would just you would not really gain anything from solving the problem. I would not expect that. Yeah. Whoops. Let's move a bit up. Okay. We can discuss a little bit how to exploit that structure. So this matrix is very sparse, so it's lots of zeros, and the way people have used to speed up the computation of that system can show you what happens. So it's a bit too far up, but it's called condensing. That's the word here. So yeah, you don't want to approach this factorization naively, and remember, in the algorithm, you will have to solve this system a number of times. And that's the expensive part. Everything else is kind of trivial to do, but solving this linear system is the expensive part. And that's, for example, what this matrix can look like. Here I made, it's a 5-state system, so it's just 5 integrators in some sense, with one input driving it, and the horizon is 20. If you remember these questions I showed in the beginning, and you have some input and state bounds. So the resulting matrix would look like this with the dynamic constraints and the inequality constraints. And the idea of condensing, some people try to explain it via linear algebra, but for anyone with a bit of training in dynamic system, there's a much easier way to explain that. It's actually just a simulation of the system in some sense. Because what is really happening is that inside your dynamic constraints, you're essentially saying that I have a linearization of my dynamics, right? The delta k plus 1 is essentially given by a times delta xk plus b times delta uk. It's a discrete dynamic system at the end of the day. And what you can do here, quite obviously, is to calculate the delta xk's as a function of delta x0 and the set or the series of delta u's you have, right? This is just a simulation in some sense. If you had a linear system that looks like this, and delta x0 is given and the delta u's as well, you could say essentially delta x1 is equal a delta x0 plus b delta u0, and then delta x2 is a square delta x0 plus ab delta u0 plus b delta u1, and so on and so forth, right? And that's really what condensing is doing essentially. If a and b are varying like this del x f del f del uf, you end up with doing sums and products of these matrices, but essentially the same story here. The bottom line is that you can express all the delta x's as a function of delta x0 and the delta u's. So that's what's happening here. And in a compact form, you could say that your delta w's they are made of the delta x's and delta w's. Sorry, delta x's and delta u's. Delta xn minus 1, and so on. All this delta w, you could write it as, or express it as a function of the delta u's, and assuming we know the delta x0 because it's basically given by initial conditions. So you can essentially write the complete set of primal variables as a linear or affine function of delta u, right? It's really a simulation effect. And then essentially you would replace all the delta w's by this here in the QP problem. So it's really a replacement. So for example, you see that B inherits M transpose BM. And then you have a Hessian in terms of delta U alone. And the same happens on the other terms. And so we basically eliminated these equality constraints, and we're left with a quadratic objective function in delta U and some inequality constraints in delta U as well. So that's the condensed QP, no more equality constraints, and you have possibly dramatically reduced the number of variables. So you imagine you have one input, for example, here, and 5 states. That's essentially dividing by 6 the dimension of the problem. And then this matrix that you need to manipulate inside the QP problem. So it lost the nabla G's, and you need to work on the active set on this constraint here. And essentially you have this Hessian here and these guys here with the different active sets. Does that make sense?
So what was the M matrix?
Right, yeah, it's this thing that comes from simulating the system. So this equation is essentially the details of writing these things here, right? You're following this, right? Yeah. And that's just a more complicated way of expressing that. If you have varings A and B's. And then what you see here is that delta xk is a function of stuff multiplying delta x0 and stuff multiplying the delta u's.
Yeah.
So I can rewrite all these variables, the delta x0s to delta xn, all the delta u's, as a constant term plus a matrix multiplying delta u.
Okay, so that A matrix, it's not the same.
No, it's not the same. No, sorry. Yeah, we call it differently if you want.
Yeah.
And M is not necessarily trivial, but you can assemble it from these things somehow. Right. So then you're left with doing factorizations of this matrix instead of this big one here with lots of zeros. And for example, in this case, like 5 integrators, one input horizon is 20. That matrix with all the condensing reduces to that thing here. So you're working with this matrix here. It still has some zeros, but not as many as before. But it's much, much, much smaller than the previous one, right? And the condensing is not, well, it's not exactly a cheap operation, but it's essentially multiplying matrices, so it's not dramatic. But that's not the end of the story. So that's one example, 5 integrators, one input horizon 20. But I'll do it differently now. I'll put 2 integrators, so 2 states, and 2 inputs, and a longer horizon, 60, well, instead of 20, yeah? So you get this matrix here. It's actually not bigger than before. Here I had, I guess, 250 elements by 250. Now I have less than 200 by 200. If I do the condensing on that system, actually the gain is not as impressive as before, right? And the problem is, I mean, you can guess what happened here. Here I was eliminating 5 states for one input. So you reduce a lot the system by eliminating the states. Here I have as many states as input, 2 and 2. So I only eliminate half of the variables in that sense. So the matrix is not as small as before. And I was mentioning that in the introduction, like the ratio between the number of states and inputs matters in what method you're selecting. This is because of these effects here, that they matter. If you have a number, like lots of inputs, these condensing techniques are not very good. Okay with that? There's another problem that, again, it's a purely linear algebra problem, but it's fairly easy to understand it from a dynamic system point of view. You have to imagine that at the end of the day, when I build my xn, for example, I will have a matrix A, that's my A matrix in the dynamics, this guy here, to the power n delta x 0, right? So what happens if this matrix A has eigenvalues outside of the unit circle? They get, yeah, they get powered n, right? So this A matrix, if A is unstable in the first place, it has eigenvalues outside of the unit circle, A power n will typically become insanely large for n large. So if you have unstable dynamics, and you try to do condensing, especially if you have slightly long horizons, you will create some extremely large terms in M, and this linear system will tend to become numerically difficult to handle. You can really create this problem in active set solvers using condensing. It's fairly easy. Factorizing this matrix here, it's basically dense now. The cubic computational complexity of the factorization is cubic with the size of a dense matrix. So you pay a pretty large price here for going from the very small matrix we had in the beginning to this one. So if you double the matrix, you multiply by 8 the computational time. And the horizon will also tend to create or be unfavorable for the condensing. So these methods using condensing, they are not very good if you have unstable dynamics, if you have many inputs compared to the number of states, and if you have a long horizon in your problem. Otherwise, you're good. That can be very effective to do that. Okay with that? Yeah?
So in earlier lectures, you mentioned that there was some advantage to having sparse matrices.
Yeah.
Is this one of the techniques to exploit it, or are there other factorization techniques?
We'll see other factorization or exploitation techniques for interview point methods. I think it's not trivial to exploit this matrix here, but I'm suspecting people have not fully finished doing these things. And it's really funny in research, you have, you know, like trends and people pushing in one direction or another. I'm suspecting there would be decently good factorization techniques for active set methods, but has not been coded mostly. So active set with condensing has been coded. In principle, so what you do on a matrix like this is a short complement typically, which is quite effective, but the structure is quite poor, so it's not obvious. On a matrix like this, there will be some tricks you could play probably, but I don't think people have really implemented that properly and checked what you gain.
So there are other patterns where you can do more?
Well, we'll see that the pattern you get from interview point method, you can actually do quite magic stuff. I'll show you a slide about that. Yeah. And you gain something pretty nice. So I'll get to that, but the way the complexity of this type of method grows with the horizon, it's actually, I think it's polynomial, I don't remember the term. I have a slide about that. But so if you increase the horizon, you pay more and more price. And you will see with the interview point method that it's linear. So if you double the horizon, you double the time. So it's not a dramatic increase. That's all about the factorization. Yeah, and there are, new results nowadays, like partial condensing, for example, where you condense some blocks and exploit the structure behind. So that's not the end of the story. but that gives you the background of what has been done. Okay, so we can jump to that. That's, I would say, the competitor for active set methods. And I would argue that at the moment, for real-time optimal control, like this approach we have been discussing, the winner tends to be this one. And again, it's not always just about the mathematics, it's also about what people have done to make this thing happen in the computer. There's a lot of coding involved, but there are some people pushing hard for this type of methods at the moment, and that gives very good codes for solving the problems. So I'll mention that. But essentially, okay, that's a rehearsal of stuff we have discussed before. So if we write the KKT conditions for a QP, you end up with this. So that's the nabla L, stationary Lagrange function, equality constraints, inequality constraints, completely slackness. So mu times the inequality constraints must be 0, and the mu's have to be positive. So we play the usual tricks. So we introduce slack variables, the S. We replace this guy by S, and the S must be positive. And we relax these guys by tau. And we form the linear system and the Newton steps. So delta W plus lambda plus mu plus S plus. So you solve this system again. So it has this very same form as we were playing with in applying entry point methods on the NLP directly. On the right hand side you have this guy with a tau that will change. And then again, prototype primal duality point solver for a QP. It's the same story as usual. So you will guess these guys, you'll compute these guys from solving that system. Now the difference from before is that these things here are fixed. This matrix, these guys are fixed. They're like the QP data, and these guys will change S and mu as you iterate. On the right hand side, these guys are fixed, and S and mu and tau will change. So we'll have to resolve this system a number of times. So you guess these guys, compute an update, then you play with the step size to keep these guys positive and have a decrease, and decrease tau when possible. Okay with that? So if I play the exact same problem as before, so again, solution is down here. I choose an initial guess up here, same as before. And I start with my tau is 1. And that gives me these equations here, or the norm of these equations would be this. And then I deploy the algorithm. So you'll see what happens. Instead of going around the active set, it's shooting for the interior, because tau is large, so it's going down here. And then tau will decrease, and as tau decreases, you basically shoot for the point. Tau decreases again, and approach this point. Tau decreases again, and you will land on that point quite quickly. Okay, so instead of following active constraints, it was going inside and then going for the final point. Good with that? Yeah.
You can see like it's a bit fast and then slow and then faster again and slower again.
Yeah. Let's backtrack then. It did that. Yeah, so what happened here is that I reduced the code reduced the tau. So whenever you reduce the tau, you're actually disturbing the Newton method. You're changing the problem, and Newton will react in one way or another. And here the tau was decreased by a factor 10, so it's quite aggressive as a reduction. So that's why the Newton is kind of going like, something happens, and kind of taking a slightly strange step. Then it's stepping quite well again, and then we decrease. And as we decrease, it also takes a strange step at some point. And goes
especially going faster, longer into the simulation you are. With the same.
Say it again.
When you keep the tau constant going faster and faster.
If you keep the tau constant, It would converge quadratically typically, at least locally. So depends a bit what you mean by faster and faster. But
just that it looks like going like a small step, next time a large step, and then a super large step. I would imagine that like opposite is what you normally do. You go quickly towards the goal and then slowly in.
Yeah. So it would mean here, for example, well, here you have this effect. It takes a large step and then small steps, right? It's not really completely obvious what happens when you have this interplay between reducing tau and taking steps. That's also why, in theory, it's a bit complex to analyze unless you reduce the steps in a very, very careful way. Yeah. And in entry-point QP solvers, people are often very, very aggressive with the reduction of tau, and it tends to work anyway. So, yeah. Okay. So same story as before. You will have to play with that system again and again, like factorize this guy again and again. And you need to reform the factorization because these guys will be updated at every round. S and mu will change. And this matrix has this signature here. We've seen that before. It's a fairly involved pattern. It's really not obvious what you should be doing with that. And what's going to happen is we'll essentially solve the problem kind of variable by variable. So essentially eliminate some variables one after another. And it's basically a few steps. In the first step, you would essentially eliminate delta S and delta mu. And by that, I mean, you could see, for example, from that line, that you can express delta S as a function of delta mu, right? So you have this times delta mu plus this times delta S equals something. And these guys are just diagonal matrices, so inverting them is trivial. And you can also see that you could here express delta S as a function of delta W in that sense, because you have an identity here. So you can guess more or less that it's fairly cheap to eliminate these two guys from the equations just by these manipulations. And from a linear algebra point of view, you essentially end up writing this system in terms of the primal and dual variables associated with equality constraints, changing this matrix here to this form here, made of the B, this guy here, and you will add this stuff here. So this is very cheap to form because this is diagonal -1. You just inverse every element and then multiply these matrices. And this stuff here is diagonal, so that's very cheap to do. And the beauty is that this matrix phi keeps the block diagonal structure. This is block diagonal, this is diagonal, and this is block diagonal. So when you form this, you keep block diagonal form. Then you can do one more step. You actually eliminate the primal variables. And what is happening here, when you see a matrix like this with symmetric and these two terms and zeros, you should have the Shor complement reflex, because that's what you do on this kind of matrix. And essentially, you can rewrite this system in terms of delta W with this matrix, in terms of delta lambda, with this W matrix formed by this guy here. So phi -1, and you multiply by nabla G before and after. That's the Shor complement of this system. And again, that's cheap because phi is block diagonal. So you can invert phi by inverting each block separately. And the blocks are pretty small. And this W, again, it's very nice because it ends up having this banded form. Small and banded. So again, that's fairly easy to factorize. You can do either Cholesky or Riccati factorization on these things. Yeah. So that's how codes tend to treat this system. So you have only essentially the factorization of these small blocks here and some matrix multiplication, and then factorize this matrix here, for which you have super good codes to treat a banded matrix like this, at least if it's positive definite. Okay with that? So what is nice here is that if you unpack everything, you realize that the complexity of doing all these operations is linear in the horizon. And so if you double the horizon, all these operations will take double the time, as opposed to the cubic complexity we had for active set solvers. You end up, if you really benchmark the problems, like the different methods on a problem, for example, an active set QP solver like QP Oasis and interior point solvers, you will see that the active set method is faster for small problems. That's the horizon length. Faster for small problems, but then it becomes quite bad as you increase the horizon. Whereas these interior point solvers, they are a bit worse for small problems, but if you start increasing the horizon, also the number of states and so on, it increases linearly. So you know that sooner or later you will beat the active set method here. Yeah, so we saw this before. It's good if you have few inputs. It's not good if you have unstable dynamics often. Another thing is that you can only treat QP problems in active set methods. Oh yeah, it's quadratic in the horizon, sorry about that. But you have this polynomial effect. I've used interpoint methods. The speed is fairly consistent. So unlike active set methods where you have sometimes spikes of the time you need to solve the problem when you have lots of changes in the active set, these guys have a fairly consistent computational time. Doesn't matter how many inputs or states you have. Stable, unstable dynamics are not a problem. And you can actually extend these methods to more complex inequality constraints than polytopes. If you, for example, if you have quadratic constraints or even LMI constraints and such things, you can extend the interior point methods. So these are two codes that do this. For this one you have to pay. This one is for free and is actually faster than this one. And this one has evolved nowadays to HPMPI, which is a new version that is faster. This still has some bugs. So it's still under development.
Are any of these part of Kasadi?
I think you can call them from Kasadi, yeah. If not, please annoy the developers until it's possible. But yeah, I think HP MPC is connected. I believe so. Okay. Yeah, I propose we stop here. There's a few more slides on like more advanced techniques. Maybe just a few words. I don't know if you've seen scenario trees in. It's in a robust MPC. So there as well, it's not in form of codes yet. I don't know if it will happen, but in principle, you can solve robust MPC with some scenario trees and write QP solvers that are extremely fast for these guys as well, provided that you parallelize the computations. If you can dispatch the scenarios on different CPUs, then in principle you could essentially solve scenario trees as fast as classic MPC problems. Yeah, that's a quick summary. So QPOSIS, we talked about that. Forces, that's it's getting a bit outdated now maybe. It's a primary dual interior point solver. HPMPC same, but it's essentially the difference between these guys is that this one, there's a lot of work done at the computer level to speed up the computations. You have also first order solvers like Fjordos. I did not explain that. It's based on proximal gradient methods. QP dunes, that's a mix of dualization of the dynamics and active set methods. It has some advantages in some cases. Yeah, I guess I'll stop here for the QP solvers. In the afternoon, we'll talk about indirect methods for optimal control. So we'll go back to the high level and look at more purely math stuff again.
Is that at 2 or
What's that?
what time?
Tell me. 2, yeah.
What was it?